Redis is a popular choice for caching due to its ability to handle millions of read and write operations per second with ease. Its operations all take place in memory, making it a straightforward in-memory cache similar to memcached. However, Redis offers much more than just a simple cache. Redis can also function as a persistent storage. This is made possible by the built-in AOF, append-only file mechanism. AOF can be enabled to persist every write operation to disk. There are two modes of AOF that can be configured when setting up Redis: synchronous and asynchronous. Synchronous AOF guarantees that every write operation is successfully persisted to disk before returning to the client. This means that Redis is no longer just an in-memory storage, and every write operation blocks until the data is successfully saved to disk. While this ensures data persistence, it comes at a cost of high write latency. In our production environment, we found that a single write operation under synchronous AOF took approximately 1 second. On the other hand, async AOF is a mode in Redis where write operations are non-blocking. Clients can still consider Redis as an in-memory storage since the data is saved periodically to disk in the background, which is transparent to clients. This mode provides very low write latency. However, the downside is that data loss can occur if a Redis node fails or restarts. Data that has not yet been saved to disk will be permanently lost. Imagine you are running a recommendation service that shows ads to users. To make sure the ads are relevant, you need to constantly retrieve real-time data for each ad. Initially, you used a single Redis instance to store this data. But as your business grew, the amount of data and queries increased to a point where the capacity of a single Redis instance was not enough. To solve this problem, you decided to use a Redis cluster. In a cluster, the keys are distributed to multiple instances to increase capacity and performance. Now there are two ways to distribute the keys in a cluster. One is client-side sharding. In client-side sharding, the Redis client itself is responsible for the sharding and routing logic. This means that the client is designed to communicate directly with the Redis nodes and handle the distribution of data. The advantage is that this approach does not rely on any additional middleware or services, making it simpler and easier to manage. The second approach is server-side sharding, which uses a middleware as a proxy. The proxy contains the sharding and routing logic to determine which Redis instance to visit for data retrieval, and requests from the ad ranking engine hit the proxy to retrieve data. In this case, the Redis client can be very thin since it no longer needs to handle sharding or routing. Official Redis clusters use decentralized sharding. Each node in the cluster maintains a local copy of the routing table and updates it continuously through the Gossip protocol. There is no longer a centralized proxy, and each Redis node contains the information needed to act as a proxy. When a request hits any Redis node, the node handling the request first checks if it or another node has the requested data, then redirects the request to the appropriate node if the data is stored elsewhere. In this episode, we reviewed basic ideas of Redis instance and Redis cluster. In the next episode, let's continue to delve into the exciting sharding algorithms. We will first go through consistent hashing, and then talk about the hash slot sharding algorithm used in official Redis cluster distribution.